Welcome to PT 772, Scientific Inquiry 2 in PT. The title of this presentation is Reporting of Results Using Statistical Analyses, Meta-Analysis, and Quantitative Synthesis. My name is Michael Ross, and I'll be taking you through this presentation. At the completion of this presentation, the learner will be able to compare and contrast a systematic review and meta-analysis, describe the benefits of a meta-analysis, explain the steps associated with the meta-analysis, and correctly interpret a forest plot associated with the completed meta-analysis. So let's just begin by reviewing the fundamental principles of evidence-based practice. Our goal here is to really try and improve and maximize patient outcomes, and we do that by developing individual clinical expertise, which all of you are developing now as you work your way through school and your internships. Our patient values and expectations certainly play a role in that. And then at the bottom, the best available clinical evidence. Can that help us with our clinical decision making? And we'll work off that on the next slide as we work our way through the remainder of the presentation. You've all seen this evidence hierarchy previously, and it's important to note that at the top of that pyramid really sits systematic review and meta-analyses. They're important because they provide the highest quality of evidence for us with the lowest risk of bias. And so the remainder of our presentation will focus on meta-analyses and how they're really an extension of systematic reviews. So all of you are familiar with systematic reviews, and those are, as you know, a very detailed, systematic, and a transparent means of gathering, appraising, and synthesizing evidence in really a qualitative fashion to answer a well-defined question. And a meta-analysis is just an extension of that systematic review, in that we're still going to use all the methodology associated with a very well-done systematic review, but then we're going to use statistical procedures for combining the numerical data from those multiple studies, again, to answer that well-defined question. But now, not necessarily in a descriptive fashion like you might see in a systematic review, but now more of a quantitative manner. One of the main concerns that we see, especially in rehabilitation literature and the studies associated with it, are studies that are underpowered, meaning that they're typically smaller sample sizes, and that makes it very challenging to really look at treatment effects. And so the benefits of these meta-analyses are that they really increase the power and the precision for estimating treatment effects, because we're taking study participants from multiple studies, we're including them all together, we're calculating these summary statistics, and that gives us a greater chance of detecting treatment effects, especially those that could potentially be statistically significant. And it improves the confidence and conclusions that we have in decision making. You know, if you have a research question, you're likely going to go ahead and you're going to find a series of papers, and some of those papers, you know, may either, support the treatment approach that you're looking to maybe be interested in, or some may not support it. But these meta-analyses really help us to improve our confidence in our conclusions and decision making by taking all of those studies that are available and really helping us determine whether or not there is a true treatment effect associated with it. On this slide, we describe the steps that are necessary for completing a meta-analysis. And those first few bullets should look relatively familiar to you, because those are the same steps that we would use to complete a high-quality systematic review. Right? We're going to develop our hypothesis, we're going to generate our PICO question, we're going to select our inclusion-exclusion criteria, we're going to select our search methods to identify those relevant articles. Again, when we think about the articles, we're to consider the population, the study methods, the intervention, the outcomes of interest. and then we're going to likely appraise those articles, and that is sometimes a part of a meta-analysis as well. So we're going to praise the quality of those articles, and we could use something like a Pedro scale for that. There are other ways of doing that, but you're probably familiar with that scale. And then really where it changes, where that systematic review really turns into a meta-analysis, is that last bullet statement where we're going to combine all of that numeric data into one summary statistic. That's really going to help us determine, in addition to that descriptive component, the systematic review, right, what's that quantitative component that really helps us draw sound conclusions. And we're going to look to determine if the data in these studies are going to be continuous or dichotomous, because that's going to help us with our data analysis. We mentioned at the end of the last slide, when we perform a meta-analysis, we're going to come up with one summary statistic that is going to allow us to either conclude that an intervention is really effective or not. And we mentioned that whether the data that we're analyzing in the studies are continuous or dichotomous, that's really going to drive how we analyze the data in a meta-analysis. So let's take a moment and talk about how we would address continuous data in a study. And just to review a little bit, data that are continuous can be measured on a scale or continuum, and they can have almost any numeric value. And so if we think about examples of continuous data, we think about things like temperature, time, distance. We may look at outcome measure scores. Maybe we're thinking about patient functional questionnaires like an Oswestry disability index score. We may think about impairment measures like strength. If it's measured through a dynamometer, that really gives us this number, this numeric value. Range of motion measures would also be continuous, as well as, let's say, something like numeric pain rating scale scores on a scale of 0 to 10. And you could think of many others that we would have in physical therapy that might fall under this concept of continuous data. And so when we have continuous data and we're trying to do a meta-analysis, really what we're going to do is we're going to look at a standardized mean difference. That's really the summary statistic that we're going to develop for the meta-analysis. Each study that we assess, we're going to come up with that for the variable of interest. This is sometimes called the SMD, and it may also be referred to as an effect size or Cohen's d statistic. And the formula for this is looking at between group differences and then dividing that by the pooled standard deviation of those two groups. And how do we interpret a standardized mean difference? Well, in a study, studies we're going to evaluate are likely going to use a p-value. But we've talked about these before, that a p-value, although it's statistically significant, the differences between the groups may not necessarily be clinically significant. And so these standardized mean differences really allow us to look at the treatment effect, put a number on that, and help us interpret that. And so if we look at the interpretation of this, we're looking at an effect size or a standardized mean difference anywhere from 0.2 to 0.49 as being considered a small effect size. Anywhere between 0.5 and 0.79, that would be considered a medium effect size, and anything greater than 0.8 would be considered a large effect size. And if you look at that formula, right, you can see, well, how would I get a large effect size? Well, one way you do it would be to have large between group differences, right, and a small standard deviation, right? Standard deviation really relates to the variance within the groups. And so if we have large between group differences, right, and small group variability, we're likely going to get a large effect size. And I'll give you an example of how this may work in terms of a meta-analysis. Let's say we're trying to determine the effects of intervention on patients who have adhesive capsulitis. And let's say we want to compare a home exercise program to a home exercise program combined with a corticosteroid injection on the effects of range of motion. And so let's say our intervention group is going to be the corticosteroid and the home exercise program. We're going to compare that to, we'll call it our control group, is just the home exercise program. And so we would look at, let's say, a change in external rotation range of motion from baseline to, let's say, 8 weeks. Right, and we determine how much range of motion changed in that treatment group, right, the group that got the corticosteroid and the home exercise program compared to our control group. And we'll just call that's that home exercise program group. So we're looking at the change in range of motion from that first group who got the corticosteroid injection, and we're subtracting that or comparing that to the amount of change in external rotation range of motion in that second control group, right, who just got the home exercise program. And so we're going to get a difference between those two groups for that study of external rotation range of motion. And we're going to divide that, right, by that pooled standard deviation, right, the within group variance. And if that number is small, standard deviation is small, and the between group differences is going to be large, we're likely going to get a larger effect size. The larger the effect size, right, the more credence it would give for that intervention strategy of using a corticosteroid injection with that home exercise program. And again, the study that may have done that we're looking at may have looked at p-values, looked at statistical significance, but in our particular case, we want to know the standardized mean difference. The standardized component is that we're dividing it by the standard deviation, right? If we just looked at differences between the two groups, that would just be the mean difference. But remember, we want to compare this with multiple papers in the study and come up with this summary statistic. And so what data do we need to come up with a summary statistic from these trials? Well, like we just mentioned, we need the group means and the standard deviations for the measure of interest, and we also need the study participant numbers. The study participant numbers are important because they allow us to weight the individual studies. The more study participants, typically the stronger a study is in a meta-analysis. And the group means and the standard deviations are going to allow us to calculate those standardized mean differences or effect size or that Cohen's d statistic. So in addition to calculating a summary statistic, which is going to be very important in helping us determine the effect of a particular treatment, we're also going to calculate confidence intervals around that summary statistic. And confidence intervals, we're going to talk about a 95% confidence interval. To interpret that, if we look at a 95% confidence interval, we can be 95% confident that the population parameter is somewhere between those two numbers. An example here, if we look at IQ scores, IQ testing scores. So if we take a random sample of 50 students at one school, and we determine what that confidence interval is, we can see the 95% confidence interval would be between 97 and 106. And the correct interpretation of that confidence interval is that we can be 95% confident that the mean IQ score for that particular population of students at that school is going to be between 97 and 106. And so we'll talk more about confidence intervals as we move forward in the presentation. But again, it's important that when we calculate that summary statistic, we have confidence intervals around it as well, because that's going to help us interpret our results with more confidence. So let's go ahead and apply this to a clinical situation. Let's say you're working with a patient following ACL reconstruction, and you're trying to figure out what's the best way to really get quadriceps strength back following ACL reconstruction. We all know that trying to get quadriceps strength back is really an important component of the rehabilitation process. And so one question we may have is the use of neuromuscular electrical stimulation in addition to a standardized physical therapy program, is that superior to a standardized physical therapy program alone without neuromuscular electrical stimulation in improving quadriceps strength following ACL surgery? So the next slide will show you a paper that we found that really helps us try and answer this question using a systematic review with a meta-analysis. And so looking for papers that would address our clinical question, we were able to find this paper titled Neuromuscular Electrical Stimulation is Effective in Strengthening the Quadriceps Muscle After Anterior Cruciate Ligament Surgery. There's many different ways of writing titles for papers. This paper, the title used, really gives you some clear insight as to the results of their trial. They're telling you up front in the title that this approach with neuromuscular electrical stimulation, that it is indeed effective in strengthening the quadriceps muscles. That's kind of cool. Now, what you don't know in just looking at the title is what type of paper is this? Is it a randomized controlled trial that just looks at two groups? Or is it a systematic review, or is it a systematic review with a meta-analysis? And so this particular paper, if you dig a little bit deeper, is actually a systematic review with a meta-analysis. And so what you find in this particular paper is all of the methodology that you would see for a systematic review, meaning that we have a clear hypothesis and a research question. We also have clear inclusion and exclusion criteria. The methods for searching the literature and trying to identify papers that met the inclusion and exclusion criteria are clearly there. And we also even have an appraisal of the quality of the papers through the Pedro scale, which many of you are familiar with. The difference here, though, is that they've applied these meta-analytic techniques to really analyze the data, to take it one step further from that systematic review where we see a descriptive analysis of the results to more of a quantitative description of the results. And so in the following slides, we'll go ahead and we'll discuss that. One of the great things about a meta-analysis is that the graphs that the authors put forward really help us understand the findings related to their results. And the graph here that you see is what we call a forest plot. And so this is really going to help us understand the results. We have some data on the slide, but we also have some visual representation as well of the data, which again really helps make sense of the results. And so we're going to take some time to review this forest plot. That really helps us understand if neuromuscular electrical stimulation is going to be effective in helping individuals regain quadriceps strength following ACL reconstruction. In looking at the graph that we have here, where I've squared off in that red box on the left, those are the number of studies that have been included in the meta-analysis. You can see the author's last name as well as the year of publication there. And then as we move across to the right, you're going to see some data associated with each particular study, as well as a visual representation of the standardized mean difference with a confidence interval. And so the standardized mean difference, I have a red arrow pointing to that. These standardized mean differences are very interesting in a post-operative study, because these 6 studies that they've included are really post-test only control group designs. And what do I mean by that? Well, if you were going to do a classic randomized control trial, right, you would take 2 groups. You would go ahead and randomize one group to the stim, one group would not get the stim, and you would evaluate the strength of the quadriceps. Let's say it's a healthy population on day 1, treat these individuals for 6 weeks and evaluate it 6 weeks later. And we'd come up with a change score for each limb. Well, we really can't do that in this particular case, because in order to get those pre-test strength measures, you'd either be dealing with the individual following the ACL tear, or we would be doing it right after surgery, which wouldn't be a valid measure. And so these standardized mean differences really relate to the difference in post-intervention measurements that are standardized as a percent of the mean value of the strength of the involved lower extremity compared to the uninvolved lower extremity. So we're coming up with a percent. Again, these are only post-test measures, but we can compare the intervention group who got the stem to the group who didn't get the stem just by looking at what percent of strength has been regained in the involved side compared to the non-involved side. And so we'll talk more about what those SMDs mean, but if you look down that column, you'll see different numbers, and that relates back to that effect size that we talked about. Remember, anything between 0.2 and 0.5 is small, anything between 0.5 and 0.8 is medium, and anything above 0.8 is a large effect size. And so you can see the scores there. They vary quite a bit, and we'll move on to the next slide and begin to interpret that a little bit more. Let's go ahead and delve into the forest plot a little bit deeper. And so we mentioned on the last slide, the far left-hand side, that vertical column, those 6 studies that were included in the meta-analyses. And as we move right, we see some visual as well as numerical data associated with each of those studies. So if we look at that first study, the Delito study, and we move toward the right, I have 2 circles there. I have a black and I have a blue circle. And so the black circle really relates to the individual standardized mean difference for that particular study or the effect size. And the lines that are horizontal to that black dot relate to the confidence interval. And so for that particular study, you can see a standardized mean difference or an effect size of 1.94 with a confidence interval of 0.85 to 3.02. And remember, when we talked about how we interpret those effect sizes, anything above 0.8 would be considered a large clinical effect. So that is probably a very important study that looks at this effect of neuromuscular electrical stimulation. And so the other thing that's important is where those dots and their confidence interval are positioned relative to those 2 lines that you see that are highlighted with the red and the green arrow. And so that red arrow, that's an important one because that signifies the line of no effect. And so if you take that red arrow, follow that line all the way down to the bottom there where I have that yellow box, you can see on the left side it has negative 0.5, and then you can see a line that says 0. That's that marker, that's the line that's marked by that red arrow, and then to the right of that you see 1, 2, and 4. Those are standardized mean differences or effect sizes, and remember that really relates back to those numbers we gave you of how to calculate these effect sizes. Remember, small 0.2 to 0.49, medium 0.5 to 0.79, and then large would be above 0.8. And so how would you get, and that red line, like I said, that red arrow really relates to what we call the line of no effect, meaning 0. And so how would you get a standardized mean difference of 0? That would mean that there is essentially no difference between the 2 groups. Remember, those sit up in the numerator of that formula, whereas the standard deviation sits in the denominator. And so to get a 0 out of that formula, 0 out of that fraction, you have to have no difference between those 2 groups. If, however, the intervention group or the neuromuscular electrical stimulation group was going to be more effective, you're likely going to have a positive number. And so anything to the right of that line of no effect, that 0 point, is going to favor the neuromuscular electrical stimulation. And so if you look at all of these studies, you can see that all of them fall, at least their standardized mean differences all fall to the right of that line of no effect, which means that, at least to some extent, all of these studies showed that neuromuscular electrical stimulation is likely to be more effective. Now, how would we know if it's truly statistically significant or not? Well, that goes back to that confidence interval. If the confidence interval includes 0, even though the standardized mean difference to the right of that line of no effect, if the confidence interval includes 0, it suggests that there is no statistically significant difference, even though the group may favor the study may favor neuromuscular electrostimulation. And so if you look at that, you can see that studies 1, studies 2, and studies 4, those are the only ones that have a confidence interval that doesn't include 0. The remainder of the studies, you can see that the confidence interval includes 0, and at least the left side of that confidence interval crosses that line of no effect. Despite the fact that all of these studies favored neuromuscular electrostimulation, we can say that studies, again, 1, 2, and 4 are the ones that demonstrate statistical significance. And so it's important to understand how that confidence interval really fits into here. And so there's another arrow at the top, that's that green arrow, and that red dotted line all the way down really represents the summary effect or summary statistic when we average up all of these 6 studies, right? And so on the far left-hand side of the screen, you can see I've put a little square around overall. And if you follow that along to the right, you'll see a large diamond. That large diamond is the summary effect or summary statistic when we average up all of the SMDs for those 6 studies. And if you take that over to the right a little bit further, you can see that the summary, the standardized mean difference for the group, for these 6 studies as a group would be 0.73 with a confidence interval of 0.29 to 1.16. And we would say that's statistically significant because it doesn't include 0, meaning it doesn't cross that line of no effect. And so, and how would you interpret that summary statistic of 0.73? Well, it's certainly moderate. It's a medium effect size, right? And it's on the high end of that medium, and it's likely approaching the low end of a large effect size. And the last thing I want to mention on this particular slide is going to be the far right-hand column that I've boxed off in red. That's the weight of each of these individual studies. Right, the weight of each of these individual studies, and how do they determine how a study is weighted? It really relates back to the statistical program that you would use that looks at the precision of the data gathered as well as the size of the sample. So if there's a more precise study and if there's a larger sample size, it's going to be given more weight. And again, you look at this slide, there's a lot going on here, but if you can understand the importance of what the SMD means, what the confidence interval means in relation to the line of no effect, what the overall summary effect or summary statistic means, and then as well as how these studies are weighted. They're not going to be weighted equally. They're going to be weighted based upon, again, the precision and the size of their sample. And so that gives us that summary statistic of 0.73, which suggests that there is a medium or a moderate effect of neuromuscular electrostimulation in helping regain quadriceps strength. Again, anything to the right of that line suggests that each of these studies suggests that there's a positive effect for neuromuscular electrostimulation. If anything was to the left of it, it would mean that the control group actually did better. We don't see that here, but you can sometimes see that as well. The other thing I want you to appreciate is the amount of variability amongst these different studies. So we have some that suggest there's a significant difference. Others say maybe an effect, a positive effect, but it's not statistically significant. And we'll talk more about that as we move our way through the presentation. So let's continue to analyze our forest plot. When you look at the visual depiction of the SMD as well as the confidence interval, you may have noticed that around that black dot that represents the standardized mean difference or SMD, there's also a gray box. And if you look at each of those 6 studies, the size of the gray box varies. And the size of the gray box varies based upon the weighting of the study. And remember, when we talked about how studies are weighted in meta-analyses, It's really based upon the statistical program, and it's really based upon the precision of the study, and really it's also based upon the number of participants in the study. And so if we look at the two studies that we've highlighted there, one in black and then one in red, the Delito et al. Study, if you follow it across to the right, you'll see that the SMD is at 1.94. It's well to the right of that line of no effect, suggesting that there is a positive treatment effect for the electrical stimulation. Also, the confidence interval does not include 0. The weighting of the study is 10.90, and so there's a respective gray box around the SMD that's consistent with the weighting of that study. If we drop down one line down to the FEL study from 2011, you can see that the weighting of that study is 25.32, and you can see that the gray box there is about twice the size of the gray box that we see for the Delito et al. Study. And all that means is that that study is weighted more heavily than the Delito et al. Study based upon the program that was used for this meta-analysis. And so again, the weighting of these studies is likely going to matter in terms of the summary effect and the summary statistic. But really understand the visual depiction of the data in terms of what that black dot means and the mean SMD, as well as the gray box associated with it, which really represents the weighting of the studies. The last thing I wanted to speak about on this particular forest plot is the degree of heterogeneity related to the results of the meta-analysis. And so that's represented on the far bottom left-hand corner of the slide. I've squared that off in that yellow box. That I-squared statistic relates to the degree of heterogeneity seen in the results of the meta-analysis. And the heterogeneity of results really relates to how similar the studies are that have been included in the study. And all things being equal, we would probably want to see test results that are probably more homogeneous, because this really relates to the fact that there's probably a more common treatment effect across the various studies. And so when we see varying degrees or higher degrees of heterogeneity, it really relates to the fact that the treatment effect was not consistent across the studies. And I mentioned that to you. If we look at studies 1, 2, and 4, you can see that the SMD is, and the confidence intervals do not cross that line of no effect. The other studies do. And so while 3 of the studies suggest that there's a significant positive effect for the NMES from a statistical perspective, the other 3 studies suggest that there may not be. And so I think that it's important to talk about this a little bit more. And so when we look at that I-squared statistic, if it's above 0.5, it suggests that there is a higher degree of heterogeneity associated with the study. Again, just means that the treatment effect was not common across the studies included. And to have confidence in your results, you would like to see low degrees of heterogeneity, more homogeneous results. That p-value as well of 0.047, less than 0.05, suggests that there are higher levels of heterogeneity involved in this particular study, despite the fact that we have a summary effect or a summary statistic of 0.73, which suggests that there is a medium to large effect for neuromuscular electrical stimulation. And so on the next few slides, we're going to talk about how the authors of this particular study dealt with that higher degree of heterogeneity, and could that be managed to some extent so that we could have lower levels of heterogeneity and perhaps more confidence in our results. So in the last few slides, we spent a fair amount of time discussing the forest plot associated with the 6 studies that were included in the author's meta-analysis. And they concluded that neuromuscular electrical stimulation is in fact effective for helping restore quadriceps strength in the early stages following ACL reconstruction. And As we all know, there are many different factors that can influence outcome following ACL reconstruction. If we just think about a few, and sometimes we call these confounding variables in terms of research, perhaps a certain age group does a little bit better than others. Perhaps individuals who have maybe fewer structures injured inside their knee, in addition to their ACL, maybe those folks do a little bit better with rehabilitation. If we think about folks who may have maybe higher fear avoidance beliefs, maybe those are individuals who may be prone to have a less positive outcome. And then finally, if we take somebody who's extremely busy at work and busy with their family responsibilities, maybe they have some compliance issues with getting to the clinic or maybe performing their home exercises, maybe that could potentially influence their outcome. And so again, from research and research perspective, we sometimes call these confounding variables, but in terms of meta-analyses, we call these moderator effects. And many times authors are going to look at these different moderator effects and determine, can they potentially influence outcome? And so in this particular study, what they wound up doing was doing a sub-analysis of those 6 studies that we talked about previously. 2 of them, they noted that they started later in rehab with the neuromuscular electrostimulation, meaning that they started after the first week of therapy. And then on the bottom there, in the yellow box, you can see that these are the studies that started early with the electrical stimulation on the quadriceps. So these are folks that started within the first week following surgery. And so the late group, again, in the blue box on top, those are individuals who started within or after the first postoperative week, while the early group started within the first postoperative week. And so take a look at the forest plot here. And before you move forward, see if you can interpret some of the findings associated with these stratifications in terms of starting the stim late versus early. Hopefully you took some time to try and interpret the slide on your own before we move forward here. But let's go ahead and try and talk through this second forest plot for this meta-analysis. And so I'm going to start with the yellow circle on the diamond on the bottom. It's the line that's titled overall on the far left. If you follow it over to the right, you'll see that diamond. And that diamond is going to be important because that is the overall summary statistic or summary effect for all 6 studies. We've talked about that previously. It's listed as having an effect size of 0.73, which is in that medium to large range. But if we begin to do a sub-analysis and kind of stratify the results based upon whether or not the stim was started later or earlier in the course of rehabilitation, we can see that the summary effects or summary statistics vary quite considerably. So let's move up toward the top. Those 2 studies that are highlighted in that blue box, those are the 2 studies that started later, after the first postoperative week, and they determined that the summary effect or summary statistic was 2.01, which is really a large effect, a large clinical effect that would really drive our decision making in terms of influencing outcome. If we look at the 4 studies that started earlier in the course of rehab within that first postoperative week, you can see the standardized mean difference or the effect size was listed at 0.44. And comparing the effect size from the early group to the late group, you can see there's really a large difference there in terms of the clinical effect. Again, comparing an effect size of 0.44 to 2.01, that should really drive your clinical decision making as to not only using neuromuscular electrostimulation, but when you would want to apply it. So on this particular slide, I've highlighted the I-squared statistics associated with the late, early, and the overall effect. At the very bottom in the red box, you should be familiar with that finding because that's the summary effect or summary statistic for all 6 studies that we talked about previously. The I-squared statistic was at 55% with a p-value less than 0.05, suggesting that there was a high degree of heterogeneity in the studies that were included. which just means that the study results were somewhat dissimilar, and that could potentially influence our confidence in the results. However, if we look at the I-squared statistics for the late and early group, you can see that that is now at 0. The p-value is above 0.05. So we've gone from having a relatively heterogeneous population to one that's more homogeneous. And so by grouping these studies in terms of late and early application of the electrical stimulation, we've decreased the heterogeneity and likely increased the confidence in our results. And so again, this meta-analysis not only helped us understand the importance of using neuromuscular electrical stimulation in terms of generating quadriceps strength following ACL reconstruction, but now this slide also tells us that applying the stimulation later in the course of rehab is probably more beneficial than applying it earlier in the course of rehab. Remember, the later application means it was applied after the first postoperative week. And so again, this can help us not only in determining the importance of using electrical stimulation following ACL reconstruction, but also the timing of its application as well. And so on this particular slide, I highlight the abstract for you from the study that we've been discussing. And you can take a moment and see how the authors summarize the results in their abstract. I've highlighted those in the green box on this particular slide. Previously, we talked about continuous data, and we talked a great deal about that in terms of the study that looked at the neuromuscular electrical stimulation following ACL reconstruction on the quadriceps. And now we'll switch gears a bit and look at dichotomous data. And dichotomous data are much different than continuous data. These are data that only have two possible values. Examples of this are potentially yes or no. Does an individual have a disease or a particular risk factor, or do they not? It could look at male versus female, again in terms of whether or not they have a particular risk factor or a particular disease process more often. It could look at age. Again, we could stratify age in terms of maybe over 50 and less than 50 and determine if, again, an outcome of event, again, perhaps a disease process or a risk factor is more prevalent in those particular groups. We could look at something like a pass-fail. This could be some type of an examination, and I think about the educational literature and the NPTE, an exam all of you will be taking and will be successful on, but it's an important measure when we know if folks are either passing or failing to determine what some of those predictor variables are. And there's others that you can think of as well, but dichotomous data, we're looking at two choices. And when we evaluate dichotomous data, we can use either risk ratios or odds ratios. And risk ratio, it really calculates the risk of a certain event happening in one group compared to the risk of that same event happening in another group. And when we look at odds, instead of risk, now we're dealing with odds. And so it looks at a measure of association between exposure and an outcome, and it represents the odds that an outcome will occur given a particular exposure compared to the odds of the outcome occurring in the absence of that exposure. And so, for example, we could look at a group of athletes, and one or half is going to get for their warm-up, they're going to participate in an active warm-up and a static stretching program. The other group of athletes, the other half, is going to just participate in the static stretching program. And our outcome of interest may be whether or not they have a lower extremity injury due to during sports participation. So we could calculate the risk for that occurrence happening, and we could also calculate the odds of that particular event happening as well. And risk and odds, they're different concepts, and really when we look at risk ratios and odds ratios, they're different statistical formulas that we would use to calculate these. And again, depending upon the population you're dealing with, one may be a bit more relevant than the other. But I'm going to tell you that in the meta-analysis literature, you'll see risk ratios probably used more. And there's probably some good reasons for that. First of all, it's probably more understandable for patients and clinicians, and it probably has a little bit more clear clinical usefulness, because when we look at risk ratios, if we see risk ratios less than 1, that means that we have a reduced risk for an outcome or that event of interest. If the risk ratio is greater than 1, we now note that there's likely a greater risk of the outcome of interest occurring. And if the risk ratio is exactly 1, or if the 95% confidence interval includes 1, that means that there is no difference in risk, meaning the incidence in each group is likely going to be the same. And just to take the interpretation of that a little bit further, if we look at a risk ratio of, say, 3, right, that means that the risk of an outcome is increased threefold in the individuals who potentially have that particular outcome of interest. And if the risk ratio is 0.5, that means that the risk ratio is cut in half in the group that we're interested in. And so, again, depending upon where the risk ratio falls in relation to 1, that's going to tell us if there's either a reduced or an increased risk. What data do we need to calculate these risk ratios? Well, we need the event of interest. And so whether it's a disease process, an injury, or an outcome, we need those numbers. We also need the study participant numbers as well. And so on the next slide, we'll generate a research question that really focuses on dichotomous data. And hopefully that'll help you understand these processes a little bit more. Let's say that you're working with patients that have cancer, and you notice that depression is a common comorbidity in these individuals who have cancer. And the question may come to your mind that, did the depression come on as a result of the individuals being diagnosed with cancer, or was depression present and potentially even prior to the individual developing cancer, and was it even potentially a risk factor for cancer? Now, we know that the causes of cancer are complex, and they're related to many different factors, including genetic factors, unhealthy lifestyles, and environmental factors. And some have theorized that psychosocial factors, including depression, may actually be a risk factor for cancer. And so let's say that your clinical question is depression a potential risk factor for subsequent cancer? And if that is the question you want to evaluate, then you would search the literature for studies that potentially would address your particular clinical question. And we'll show you a study that we came up with that helps us address that particular clinical question. The study that we found that addresses our clinical question is titled Depression and Cancer Risk, a Systematic Review and Meta-Analysis. This was published in 2017, and as you see in the title, it really tells you that this is a systematic review and meta-analysis, unlike the previous paper that we looked at for the neuromuscular electrical stimulation, where you kind of had to dig around the paper a little bit to determine, did they do a systematic review and or meta-analysis. And so in this particular paper, they reviewed a series of papers that looked at the association between depression and cancer risk. And on the next slide, we'll show you the forest plot that really provides the key data for the relative risks that they calculated, and we'll see if we can kind of make some sense out of these findings. So this slide presents the forest plot of depression and cancer risk in the study that we just introduced to you. On the left, you'll see the listing of the studies that were included, and there were 23 studies included in this particular meta-analysis. On the right, you can see the relative risks and the weighting, and then on the bottom, right, it shows you the risk ratios from 0.1 to 1 and then over to 7. I'm not sure why they used anchors of 0.1 and 7, but the key point here is really that our line of no effect for risk ratios is now a 1. We talked about calculating standardized mean responses, standardized mean differences, or effect sizes, we were looking at a line of no effect of 0. And so remember, in this particular case, a relative risk of 1 suggests that there's no difference essentially in cancer risk between individuals who are depressed or not. That's what that would mean. If it's to the right of that particular line of no effect, that means that there is an association between depression and cancer risk, a positive association, and if it's less than 1, it really means that there is no real risk associated with it. In fact, the risk is likely going to be reduced. So take a moment, review this, and then we'll kind of come back together on the next slide and we'll go over it in a bit more detail. So hopefully you get a chance to review the forest plot that looks at depression and cancer risk, and we've highlighted again a couple different points here. The red arrow highlights that line of no effect, and remember, when we look at these different authors and we look at the author's name and their date of publication and we move toward the right, we're going to see that that black dot surrounded by a gray square, and then to the right and left of that, horizontally, we're going to look at those black lines. That's going to indicate the 95% confidence interval. And if that 95% confidence interval includes 1, it's essentially a non-significant finding. And so as we work our way down these particular studies and we look at those risk ratios, you can see that several of them cross that line of no effect. When we move our way to the right, I've circled that in black. Those are the risk ratios and the 95% confidence intervals, the numbers associated with those for each of these particular studies. And you can see that, you know, they vary a bit, right? Most of these studies are essentially to the right of that line of no effect, which suggests that there is an increased risk of cancer in individuals who are depressed. If we look at those studies that are to the left of that, and there's, I think I've seen maybe 2 there, that suggest there's actually a decreased risk of cancer in folks who are depressed. And so if we look down all the way at the bottom at that diamond that I have circled, that's the overall summary effect or summary statistic in terms of a risk ratio. You can see that that diamond sits just right to the line of no effect, and the green arrow points out a risk ratio of 1.15 with a confidence interval of 1.09 to 1.22. So that tells us that there likely is probably a small but positive association between depression and cancer risk. And on the next slide, we'll highlight some of the concerns with respect to heterogeneity, but hopefully you have some understanding of what this slide is presenting. And this forest plot, again, is something we see commonly in these meta-analysis papers. And so for the previous study that we talked about the neuromuscular electrical stimulation, we talked about this I-squared statistic, and it relates back to the heterogeneity of these studies. And remember, when we talk about heterogeneity, it just tells us that if it's above probably 50%, it just tells us that there's some dissimilarities between the results of these studies. And if you look at, right, this forest plot and you look at where those relative risk ratios sit in relation to line of no effect, you know, we don't have an extreme amount of variance, but there certainly is some variability in the results of these different studies. And so that I-squared statistic is at 60.8. That suggests there's a high degree of heterogeneity for these studies, and you can see that associated with the p-value as well. And on this slide, we post the abstract for you again from that particular study, and we've highlighted in that blue box the results section of the abstract so you can see how they write this up. And they essentially conclude that depression was significantly associated with an overall elevated cancer risk. And if you look at the conclusions as well, they talk about further research really looking to address some of these confounding variables or moderator effects, as we described them previously, in terms of other risk factors like cigarette smoking, alcohol use, physical activity. So controlling these variables would really help you determine the true effect of depression and whether or not it is a cancer risk factor or not. The last thing I want to mention is that if you are interested in doing a meta-analysis, you'll need a statistical program to assist you with that. There are several out there. Some are free and some are at a cost, but the one that continues to be seen in the literature is this program called RevMan. It's through the Cochrane Collaboration Group, and the first link on there is the download site to download the software on your computer, and then the second link on this particular slide is a YouTube video that provides a tutorial on how to enter data into the program. And so utilizing that is going to help a great deal in your data analysis, whether they be continuous or they be dichotomous. Thank you so much for your time and attention.